Okay, folks, we should be pretty much closed out on the quiz at this point. So let's go ahead and start moving ahead with material for today. So what I want to do is pick up with where we left off more or less on last night's video, which is a discussion of bond polarity and molecular polarity. And this comes out of our discussion from the video of electronegativity. All right, we're going to review all that real quick. All right, so let's take a look at just one of the simple bonds that we looked at in the video. We can have, for example, a hydrogen atom bonded to another hydrogen atom through a covalent bond like this. All right, and we can look at this and remember that the electrons are being shared, and they're being shared equally because each hydrogen has the same affinity for that electron pair as the other hydrogen. So as a result of that, we said in the video that this was, if we focus on the bond alone, a nonpolar bond. And we could also talk about the molecular polarity. In this case, simply because the nonpolar bond is there, and it's the only bond we need to worry about, we can also say this is a nonpolar molecule. Now let's look at the other extreme here. What if I had a covalent molecule involving a hydrogen and a fluorine sharing an electron pair? Okay, so we could draw it out as a Lewis structure like that. Now here we have to think about the fact that there's going to be an electronegativity difference between these two atoms. Okay, you'll remember from the video that fluorine is the most electronegative element. So what that means is it's going to have a tendency to pull the bonding electrons in toward itself. So these bonding electrons are going to have a tendency to want to move in that direction. Okay, so as a result, what's going to happen here is that the fluorine is going to take on a partial negative charge, and the hydrogen is going to take on a partial positive charge. So that little delta there means partial. Okay, if this were an ionic compound where we actually had one element stealing the electrons from the other, then we would actually have full-on charges here. So we look at this in this case and we'd say, okay, is the bond polar or nonpolar? Well, there's no doubt here that because of this unequal sharing of electrons, that the bond will be polar. So we'll say that's a polar bond. So remember, when we say polar, what we mean is that there's going to be a charge of a nature like a negative on one side of the molecule or bond, and a charge of the opposite type on the other side of the bond. Okay, now since, again, this only is one bond across two atoms, we can also say by default, this is going to be a polar molecule. So the molecule itself, as we said, will have a net dipole moment, or a fixed separation of charge in space. And we could show that, for example, by an arrow, and I think I did this in the video, showing the direction of the charge flow. And also I could show it as kind of a simple dipole here, where in this case, I have a negative end of the molecule and a positive end of the molecule. All right, so these are different ways I could represent that. All right, so that's more or less where we left off toward the end of the video. Is everybody okay with that? All right, so let's take a look at some more complex examples here. Now, when I say more complex, really the only level of complexity that we can deal with is going to be, of course, more complex Lewis structures and VSEPR structures. Okay, so let's look, for example, at boron trifluoride Bf3. Now, that's one we've seen before. That's boron with the infamous incomplete octet. Okay, so you'll remember that we could draw a Lewis structure for that by putting boron in the middle. And I could just put a fluorine on either side of it like that. Make our bonds. We end up getting 1, 2, 3, 4, 5, 6. All right, so in this case, we've used up all the electrons. Boron's left with an incomplete octet, but that's okay because boron's fine with that from an energetic perspective because boron has a happy formal charge of 0. Now, if you look at this molecule, I've also kind of intentionally drawn it this way because I've shown you here the VSEPR geometry as well. So again, this is an AX3 situation. So we know that in an AX3 situation, the bond angles are going to be 120 degrees all the way around, okay? So that's what geometry? We call that a trigonal planar geometry. Now, here's why this is important. I can now look at this thing from the point of view of either the bond or the molecule in terms of polarity. So if you look at the bond, you're going to see that I've got a polar bond. So I'll just focus on one bond here. I've got a delta negative on the fluorine and a delta positive on the boron because fluorine is a lot more electronegative than boron is. I can do the same out here for this fluorine, and I can do the same for this fluorine. So obviously, I have a polar bond, or a series of polar bonds here. But what about the molecule? Is the molecule polar or nonpolar? This is where we got to look at two things. I need to look, firstly, at the bond polarity. And if I've got bond polarity, then the opportunity for a polar molecule is there, but it doesn't guarantee it. Because the next thing I have to do is look at the three-dimensional geometry as I've shown it to you here. So if you think about this in terms of forces, if you will, I like to think of this in terms of like vector addition. So if you're like a physics person or an engineering person, this should kind of make sense to you. So I'm thinking about these as almost being vectors here in three-dimensional space, in this case across a plane. Now, anybody in the physics and engineering side, if you draw these as vectors in space like this, what are the vectors going to do? Are they going to add or cancel?
Cancel.
They're going to cancel each other out. Another way of thinking of this, if you're kind of not in that world, is think of a three-way tug of war here, where essentially I've got three ropes and they're tied together in the center where the boron is, and I've got people of equal strength pulling on those ropes in this geometry. Now, is the knot in the middle or the boron going to move if I'm applying the same force across all three? No, it won't. And why is that? It's not that we're not applying force, it's the fact that the forces all cancel each other out. So in this case, the charges, if you will, because of the orientation of this molecule in space, are going to cancel each other out. So as a result, even though I've got a series of polar bonds here, I'm going to have an overall nonpolar molecule. Okay, so just because we have polar bonds doesn't necessarily mean we're going to have a polar molecule. All right, so everybody kind of sort of see what's going on here. I mean, this is important because you really can't calculate or predict molecular polarity unless you've got a three-dimensional geometry. So that's another reason why going from a Lewis structure to a VSEPR structure is really important for us in terms of understanding what these things are really doing. Okay, let's look at water. Not sure if we ever did a Lewis structure of water. I think we did. But if you just do a Lewis structure of water, here's what it's going to look like. And again, you can verify this. We've done enough Lewis structures that I don't think I need to go over it. Now, if you look at this thing, look at its parent geometry here, okay, or electron domain as Chem 101 likes to call it. What's the parent geometry there? Well, you got 4 electron pairs around the central atom. Maybe you want to jump out on what the parent geometry on that is. It's going to be linear, bent, trigonal planar, tetrahedral. What are we looking at here for a parent geometry? What's an AX4, guys? No, somebody knows it. What's an AX4?
Tetrahedral.
Tetrahedral. Thank you. Tetrahedral. Okay, so that's your parent geometry there. But remember what we do. What we do is we kind of cover up the non-bonding electron pairs and see what we have left. So another way I could actually draw this in terms of a VSEPR type diagram is I could have the bonds coming down like this. And then what I'll do is I'll just have the electron pairs up here. And now I'll kind of put them like this and recognize that one of them is kind of coming out at you, okay, which I can kind of put in like that. And the other one's going into the plane of the screen here. Okay, so as a result, if I cover those up, you guys know that the actual geometry is called a bent geometry. And essentially the bond angles here are going to be somewhere around 109.5. We'll call it about 109 degrees. You know, it's actually going to be a little bit less than that because the electron pairs that are non-bonding take up more space and scissor the bond in a little. But the point is, we actually have a bent structure. Now, if you look at this, let's look at the bonds. Okay, So oxygen is going to carry the partial negative charge because it's more electronegative than hydrogen is, and the hydrogens are each going to carry a partial positive. Okay, so what's happening is if I think about my vectors now, my vectors are moving in toward the oxygen here. So if I think about this, are the vectors kind of working together or are they canceling each other? Look at the directions the arrows are pointed. Are they kind of working together or are they canceling?
They're working together in the direction
Yes,
of oxygen.
they're working together. So what I could do is actually I could draw this thing with a dipole here where I could put a positive end and a negative end on the molecule like this. And if I have that, I've got a net dipole moment. Okay, so this turns out to be a polar molecule. So the bonds are polar and the molecule is also polar. Okay, so here's one where we have polar bonds and we also have a polar molecule because the net dipole moments are working together. Well, I should say the dipole moments are working together to give me a net dipole moment across the molecule. Okay, we'll do one more of these. How about something like carbon dioxide, CO2? Okay, so CO2, we know how to do the best Lewis structure for that. We've done that one several times. Oxygen, oxygen, then we put some double bonds in there to minimize some formal charges and get electron pairs to everybody who needs them, octets, if you will. All right, so if you look at this, oxygen is the second most electronegative element. So it's going to be pulling the electrons away from the carbon. So that's going to leave a partial positive charge on the carbon, a partial negative charge on the oxygen, a partial negative charge on the oxygen. Now, if you look at this, this is obviously going to be a linear geometry. Okay, 180-degree bond angle. Now, if you do that, take a look again at the bond polarity. Do we have polar bonds? Yeah, we do. Now, how about the molecules? So again, we kind of have to look at the net dipole moment. Okay, so what's happening here? Well, if I kind of draw my dipoles here, it looks like I've got something that's doing this. Okay, so if you take a look at this, are those dipoles canceling each other or working together? Look at the direction of the arrows, canceling or working together.
Canceling?
Yes, sir, they are indeed canceling. So what do I know about the molecule? Is it going to be polar or non-polar if the dipole moments cancel?
Non-polar?
You got it. Very good. So here's another situation where we have a polar molecule and a polar bonds, but a non-polar molecule because of the canceling of the dipole moments. There's no net dipole moment here. All right. So this kind of begs the next question. This is kind of moving into what I like to call a real world application. So we can ask the question, why is molecular polarity important? So it's going to help us to explain properties. Okay, so we can look at various properties of molecules. These are measurable properties of molecules. For example, things like physical state. In other words, at a given temperature and pressure, is something a solid, is it a liquid, or is it a gas? Okay. Another physical property we could talk about is going to be solubility. In other words, is one species going to be soluble in another species? And if you're in chemistry, that's really kind of important to know, right? So let's take a look at some examples here. So let's just compare two molecules, two very simple molecules. I'm going to compare methane, which is CH4, and I'm going to compare that to water, H2O. Okay. Now, it's at normal temperatures and pressures, okay, CH4 is going to be a gas. At normal temperatures and pressures, water is going to be a liquid. Okay, I think everybody knows that. Now, you might say, okay, we can base this on molecular weight, right? So it makes sense that the heavier molecule should be the one in the more condensed state. So we'd think that, okay, if water is a lot heavier than CH4, then it makes sense that it ought to be a liquid, right? So let's see how that pans out. So I went and got molecular weights on these things. CH4 is about 16 grams per mole. Okay, so that's molar mass, just like you've been calculating all semester. Water is about 18 grams per mole. Okay, so are these appreciable differences in molar mass? No, not really. I mean, we're talking about, 2 grams per mole difference. So it's really negligible when you get right down to it. These things almost have the same molecular weight. All right, so we can't really make an argument for why CH4 is a gas and water is a liquid based on molar mass alone. Okay, but could we actually say something about the state by looking at the structures of the two molecules? Yeah, turns out we can. So let's just take a look at CH4 here. So I'm going to show it in its tetrahedral state because we know that's how it's going to be. Okay, so there's a tetrahedron. And water's bent, right? We just did water. So we saw that water kind of looks like this. Okay. And now what we can do is say, all right, let's look at dipole moments. So let's look at each one of these molecules and see what we got. Now, as it turns out, carbon and hydrogen have almost the same electronegativity. I honestly don't know off the top of my head which one. I think carbon is a little bit more electronegative. Let's say it is, but they almost have the same electronegativities. But let's just go ahead and do it this way. All right, so let's say even though these electronegativity differences are minimal, we can say that we have a very mild bond polarity here. But because of the tetrahedral nature of this thing, okay, are the dipoles working together or are they canceling each other out? Looking at the geometry. What can we say about the bond dipoles? Are they canceling or working together in this case? Look at it based on the symmetry of the molecule, right? I'd say based on the symmetry of the molecule, these things are actually canceling each other out, okay? So the bond dipoles are canceling. If the bond dipoles cancel, what have I got? I've got a nonpolar molecule. Now let's look at water. We've already kind of talked about water. We know what's going on there. The oxygen is going to be taking the electron pairs in closer to itself. So as a result, I'm going to get a delta plus on each hydrogen and a delta minus on the oxygen. So as a result, I've got a net dipole moment. We kind of drew this in terms of a dipole, right? Where I can actually have a negative end of the molecule and a positive end of the molecule. And again, this is because the dipoles are working together. So I have a net dipole moment, okay? So as a result, I've got a polar molecule. Okay, everybody see why one's polar and one's nonpolar? Any questions about that? So here's the situation. If a CH4 molecule comes near a CH4 molecule, since those dipoles cancel, there's not really any net charge associated with that molecule. So the molecules are not going to really have any major attraction to each other. Okay, so we're going to talk about weak attraction here between molecules. In the case of water, what can happen? If I just represent these as our dipoles and I've got one water molecule looking like this, and I have another water molecule, what could happen? Well, the neighboring water molecule could kind of come up against this one and it can orient its negative pole up against the positive pole of its neighbor. Now, if I put a positive charge and a negative charge kind of next to each other, are they going to repel or attract?
Okay.
Attract, you got it. So I'm going to have essentially almost like a little bond between these two things. There's going to be an electrostatic attraction. So what does that tell us? Well, it tells us that water molecules are sticky toward other water molecules. They kind of want to stick together because of these attractions that we can form between these opposite dipoles. Okay. So when that happens, water molecules want to get close to each other. And if they want to get close to each other, they're going to move toward a condensed phase. Oh yeah, like a liquid. Okay. So this is our explanation as to why water is a liquid at room temperature and standard pressure, and CH4 is a gas. Okay, water molecules can stick to each other. CH4 molecules really can't. Okay, does that make sense? So this is a nice example because we can kind of take what we've already learned about the structure of the molecule in three-dimensional space and define whether it's polar or not polar, and then talk a little bit about actual properties that we can observe. So here's another solubility one. I'll just throw this in here real quick. So this is actually a real world thing. We might want to talk about the solubility of CO2 gas in water. Now, this is kind of interesting because people have talked about, okay, CO2 is a so-called greenhouse gas, right? So it's contributing to climate change. So people have thought about, okay, how can I take carbon dioxide, for example, in the atmosphere and move it somewhere else where it can't do us harm? So one option that people have thought a lot about is using water as a CO2 sink. So in other words, can I put a lot of carbon dioxide into water under normal pressure conditions? Well, we can kind of sort of answer that question. Okay, if I draw my Lewis structure, or rather my geometry of CO2, and compare that to my geometry of water. Okay. One thing we found is that the CO2, right, the dipole moments are going to cancel each other. So there are my two dipole moments. So there's no net dipole moment. So we can say this guy is nonpolar. But we also know that water does have a net dipole moment, right, which we've seen before. So I can actually draw a molecule of water like this with a negative end and a positive end. Now, here's the interesting thing about this. If I try to introduce a nonpolar molecule like CO2 into water, is it going to want to be there? Well, if you think about it, water's going to kind of form a tight network with itself, right? Because you've got those dipole moments, like I just showed you, that can interact with each other. So water is very clubby in that sense. Now, if I take a nonpolar molecule that doesn't have a net dipole moment, like CO2, and try to put it in there, what's water going to do? Well, water's going to exclude it. Okay, because the CO2 doesn't have a net dipole moment, so it can't wiggle its way down into the water structure down there, because the waters are all saying, okay, we got these charges here and we're all happy, and you're not going to break these charges up because you don't have a charge either. Okay, so as a result of that, a nonpolar species is not going to be very soluble in a polar species. Okay, so this is actually shown in terms like dissolves like. You've probably heard that before. Okay, so if we say like dissolves like, what we're really saying is that polar things like to dissolve in other polar things, and nonpolar things like to be with other nonpolar things. Okay, but polar and nonpolar really don't mix. Okay, and that's kind of the other little witticism we could use. You've probably heard water and oil don't mix. Well, that's because water is polar and oil is nonpolar. And you know that if you try to mix water and oil together, they're going to layer out, right? So water will be on one layer and the oil will be in the other layer, okay? There's just not any chance of much miscibility between those two. So basically, carbon dioxide under normal circumstances is not going to be very soluble in water because of their polarity difference. Now, that doesn't mean I can't get carbon dioxide gas into water. I can. The way we do it is we increase the pressure. And that's what you get when you get a carbonated beverage, right? If you carbonate a beverage, what you're doing is you're actually forcing CO2 into the beverage under high pressures. For example, if on a warm day you open up a 2-liter bottle of Coke, all the fizzing comes back out, right? That's because you reduce the pressure. So all the CO2 is trying to get back out. All right, so this just gives you a couple of different examples of how we can actually take molecular polarity and structure and relate it back to actual properties of molecules. All right, any questions about that? Now, I was just going to chime in one more thing before we head over to Chem 101. Some of you guys asked last time about when our final exam is, and somebody was actually kind enough to drop it into the chat, which I don't see it because I'm usually on one screen. But just to reiterate that, it's going to be on Monday, May 17th at 10:30 a.m. All right, and it will be administered on Chem 101, just so you guys know. Now, don't worry, if you miss this, I'm going to send an email out with everything you need to know. Okay, so you'll get reminders about when things are due, like when the homeworks are due and when the exam will be. So the other good news is that I think as of Friday, as in day after tomorrow, I think we can wrap the course up. I think I'm going to be able to get through hybrid orbitals, which is kind of the last major concept I wanted to deal with. So the nice thing is you guys are going to be basically chemistry free for the last week of the semester, unless somebody objects.
Professor, I have a question about our homework.
Yep, go ahead.
So I know the homework is worth of 100 grades of our points, but like, how do you determine like how much out of the 100 do we get? Is it just based on completion, or is
It's
it
based
like
on correct completion. So what I'm going to do is I will go into, just like you would in Chem 101, I'm going to go in and get a total homework score. And it's going to give me the percentage over all the homework that you did that's complete. Okay,
Oh,
and then
okay.
that's the percentage I'm going to dump in out of 100%.
All right,
Yep,
thank
that's
you.
how I'll do it. And that's why I give you like 3 to 5 chances to get them done. So that way you have the opportunities, if you get it wrong, to take the feedback and correct your answer. So yeah, shoot for correct answers there. That's what you want, because that's what's going to get you the credit. So yeah, stay on top of the homework, guys. I know a lot of you have kind of decided to hold some of it back as a means of studying for the final, which is a fantastic idea. But I would say definitely use next week as an opportunity to get that done, so you know you're good. All right, so let's go back to some in-class problems here. And we got bond polarity here, about 14 minutes worth, so you'll have a little time to work on this. And it's basically just going over what we've just done.
I also had a question.
Sure.
So for the in-class work that we do, that doesn't count like toward our grade?
No, not at all. It's just practice.
Okay.
Yep. So if you get that wrong, it's not held against you in any way, but it's definitely to your advantage to do it because it's practice.
Will there be an extra Friday quiz?
No, we already did that. But I think for Friday, what we will do is I'll just do a regular 5 for 5 since, I want you guys to come to the last class. So, but yeah, we had our last Friday quiz last Friday. That was number 11. That was a good question. So yeah, there will be a regular old daily 5 for 5 on Friday. And just a reminder to you guys, watch the last video on hybrid orbitals. That will finish the videos for the semester. All right, folks, if there's no other questions, I'm going to go ahead and sign out. You got a few more minutes to work if you choose to do that. So I'll leave it up and running. Everybody good? All right, we'll see you guys on Friday.